let me give another example of a natural boundary condition. Okay, another example of a natural boundary condition is, let's actually for both cases set this mixed boundary condition, dw dx plus al times w equal to bl, and so this is at x equal to 0. The derivative plus bl, ar equal to br at x equal to 1. So this is the type of boundary condition that involves both the value of the function and the derivative of the function. Alright, so if we have this kind of boundary condition, it's similar to the derivative boundary condition in the sense that I actually don't know the value of w at the boundaries. Right, so what I have to do is I have to find a way to impose that in a natural way. So let's again start with the integration by parts. And now this is equal to 0. Integration by parts gives me again v times dw dx from 0 to 1 minus the symmetric form and plus my old linear form. Alright. Now, what can I do to that? It turns out neither do I know, right? I actually don't know dw dx. I also don't know v. So what can I do? Remember, the objective is to turn this into a symmetric form, right? So what can I do with this term? How can I make this non-symmetric term now symmetric? Yes?
WDX one is L minus AL.
Right. So actually, we can use the boundary condition to actually turn this into two terms. One term is actually symmetric. The other term doesn't depend on w. Right. So this is dw dx at the x equal to 1 is actually equal to br minus ar times w. Right. We can see this becomes two terms. One term, the first term, v times br, is not dependent on w, so it can go into the linear form. The other term is ar times w and times v. That's perfectly symmetric, right? So that actually makes it perfect, right? So one of these terms can go into the bilinear form. The other term goes into the linear form. Similarly, let's see, minus is just equal to BL minus AL. It's going to be equal to minus plus AL. Now this is R not K, WV, right? So we ended up having both modified linear form and bilinear form. So my bilinear form is going to be now having a minus product of the derivatives and minus AR times WV at 1 and plus AL times WV at 0, right? So this is my bilinear form now. Okay, and my linear form is going to be integration of VF dx plus BR times V1 minus BL times V0, right? So this is equal to 0. Okay, so basically we are deriving the boundary conditions depending on if it restricts the degree of freedom or not. It either is imposed as a constraint or it would modify the weak form by modifying either one of these two terms, bilinear form and linear form, or both of them. All right, make sense? Yes?
Is this going to be negative semi-definite or positive semi-definite? Because we have a liquid sign.
Right. So here, it depends on the sign of A and B, right? So here I would have a negative definite bilinear form only if both A is greater than 0, both AR is greater than 0 and AL is less than 0. Right. So that's actually what that's the kind of boundary condition that makes sense. So as you remember, the heat equation represents the mixed boundary condition for the heat equation represents the heat conduction rate at the boundary being a function of the temperature, right? So if you have AR greater than 0 and AL less than 0, it means the heat rate, the rate of heat going out of the boundary is increasing function of the temperature, which actually makes sense. If the heat flux is actually a decreasing function of the temperature, it would create some unnatural solutions, and that corresponds to a non-positive definiteness of this bilinear form. Right. So there is actually something, some physics you can say about how the bilinear form should be. All right. Okay, that's a good question. Any additional questions?